Okay, so hello, today we are going to discuss the two approaches to the same problem, to the problem of particles in a box. So namely, the first approach is statistical physics, micro, canonical acts, and Sambu. In this guy, what we are doing, we are fixing energy, and for fixed energy, since there is only several microstates with the same, several microstates with the same macro energy, thus we can construct a probability density function just as if we are calculating the probability of obtaining one or the other result of the dice. Yes, we are just taking 1 divided by number of state, and omega would be just the number of possible state. Thus omega is just obtained over integrating over the whole phase space, and basically after doing some we can just calculate the any average of any function we would like to investigate. And knowing this, what we can also calculate is just the entropy, since entropy is connected with a Sharon entropy by this constant Kb, and entropy is obviously the logarithm of number of states. And for ideal gas, when the Hamiltonian is just given as a quadratic form of momentum, so p squared divided by 2m, we just obtain as a omega this integral for energy which are between two energies. So energy slightly above our fixed energy and slightly below, which should result in just two volume of the spheres in our f-dimensional space, when f-dimensional space is just f is just the number of degrees of freedom. In our case, since we are moving in 2 dimensions, this f is going to be 2n, because for each particle has two degrees of freedom. And knowing, we just calculated this entropy. Entropy is looking like this, and knowing entropy, now it's easy to take the derivative of entropy with respect of energy and later with respect of volume, and what we will obtain is just the well-known formulas for ideal gas. So PV equals NKBT, or the energy equals NKBT for 2 degrees of freedom of each particle. And what should we do now? We would like to just check whether the same conclusion can be derived from very simple molecular dynamics. Since this is very simple, this is why I called it quasi. We have particles in a box, they are moving freely. Let's assume some very peculiar initial conditions, since I would also like to investigate how this velocity, for example, and also the direction of velocity is changing with time. And let's calculate the pressure. Pressure is calculated simply just as a force divided by the area. In our case, area would be just the circumference, so it's just the length of x twice and the length of y. And how about the force? Force is going to be the change of momenta of each particle multiplied by time. So what we are doing here is just counting the change in momenta, and each time the particle is hitting the wall and multiplied by time, it should give us the force which was exerted on the wall. And okay, it would be just the pressure. The energy is going to be just the sum of the kinetic energy of particles. I am just putting Kb equals 1, m equals 1. I'm assuming all the collisions are elastic, and what is more, the initial magnitude of velocity is just the random variable with mean equals 1 and some standard deviation which can be easily modified. And the question is, the last question I would like to address now, is whether the calculated pressure and energy are related using this volume. And volume is of course assumed as the area of our box, since the volume should be just the product of x and y, just the volume. And is this particular equation valid? So can we does this equation hold this? So is the pressure calculated in this very naive way, it's the same as energy calculated as the sum of the kinetic energy of particles divided by volume? And let's check this quickly.